In this problem, we want to create a function that is going to be able to find all of the factors of a given integer that is put into the function. And additionally, it's going to have a second output that is going to indicate whether the input integer was prime or composite. So first we want to create a flowchart that is going to guide us in writing our code that's going to create this function. But before we even get to the flowchart, let's think about if we were to do this by hand, what would be the method that we would use in order to factor a given integer? And then we can use that as a starting place to write our flowchart, which we can use to write the code. Always what we want to do is get something working first in the flowchart and the code, then we can come back and refine it, we can optimize it, but we want something that works as our first step. So let's see, how could we do this by hand? Let's say we are given, 6 as our input. And now if we sat down and did this by hand, what would we do to figure out what are all the factors of 6? Not necessarily a unique way to do this, but we can use kind of a brute force approach first, where we could think about it. Okay, we have the number 6. Let's try different numbers, obviously less than 6, and see if they divide 6. So we can start at the beginning. Does 1, let's assemble our list here, is 6 divisible by 1? Yes, well, every number is divisible by 1, so that's always going to be in our list as we're looking forward. Then we could say, is 6 divisible by 2, evenly divisible by 2? Yes, 6 divided by 2 is 3, so yes, 2 makes our list. Is 6 divisible by 3 evenly? Yes, 2 times, so 3 is on our list. Is 6 divisible by 4? No. So that's not on our list. 5, no. 6, yes. Also, every number is divisible by itself, so that would always be the last number on the list. So 1, 2, 3, and 6. And is 6 a prime number? No. So we should also have a 0 there. How do we know it's not a prime number? Well, it was divisible by numbers other than itself and 1. So in this case, namely 2 and 3. So it's not prime, it's composite. What if we have another number? Well, let's just say 11 as an example. We know it's prime, but let's still go through the motions. Is it divisible by 1? Always. 2, no. 3, no. 4, 5, 6, 7, 8, 9, 10. All of them no, but it is divisible by 11. Is 11 prime? How do we know it is or is not? Well, we can look at the list of factors. We found 1 and 11, only itself and 1. So yes, 11, we will have a prime number. And let's look at one more. Let's look at, say, 10. So it is divisible by 1. 2 divides it evenly, not 3, not 4. 5 does divide it evenly. 6, 7, 8, 9 do not. 10 does always. And we have, besides itself and 1, we do have other factors. So no, 10 is not going to be prime. Okay, so this approach will work. We'll see it's not the most elegant way to do it, but we can go back and refine it if we really want to. But we can get something that at least works that's going to tell us definitively what are the factors of our number and is it prime or not by really just testing, is it divisible by numbers starting at 1 up to itself. That will guarantee that we're going to find its factors. Now, again, it could be more work that is really necessary, but at least it's going to work as a first step, as a first version of this. So let's see how a flowchart can be made that is going to reflect that. So we're going to be given an integer input. So that's going to be the top here. We're giving an integer, it's a scalar, and I'll just call it x. So that's supposed to be integer scalar x. Okay, so let's kind of think of a bigger picture here. We're in the loop section, so obviously we're going to use a loop, but in general, we don't know necessarily should we be using loops or conditional statements or what. So let's think about what the process we did by hand was. We repeated the same type of test over and over and over again. So like in the 6, is it divisible by 1? by 2, by 3, by 4, by 5, by 6. We did the same general process over and over and over again. So I would say that thinking about repetition, that's going to say we probably want to use some sort of loop to do this. So we're going to have two outputs here, the list of factors and if it is prime or composite. Basically a binary 1 or 0 if it's prime or composite. So what we can do is start our list. So we're given x, then we can say our list, I'll call it LIS. And generally when I'm naming variables, I don't want to necessarily use the full word, or maybe I'll purposely misspell it or something. And that's because I don't want to accidentally define a variable with the same name as a built-in function in MATLAB, which possibly list is, because there's so many toolboxes, list could be. So I'll call it LIS for list. So I'm going to establish list as 1. And we'll see why in a second here. So this is going, LIS is what I'm going to call my list of factors. Now we can see here from just the 3 examples, 1, well, is always a factor. So automatically 1 is going to be the first element in our list. So we could say that list is 1. Alternatively, I could just say it's empty, would be another way to do this. And we'll see there is a difference in how we are going to code it up. Actually, I'll stick with empty for now. I think it's going to be a little bit more straightforward when we're going through the loop to see what's happening. All right, so we're going to add to the list whenever we find a factor, starting at 1, and we can go all the way up to the number itself. So we can, since we want to try every integer from 1 to the given number, we can have a counter or an index that does that sort of thing. So I'm going to establish some indexing variable I'll call k, which is my usual go-to for indexing variables. And what the k is going to do is it's going to count up from, well, 1, as I established it here, to the number itself, to x. And we're going to try dividing our given number by this k. So k is going to change its value from 1 to 2 to 3 to 4 to 5 to 6, etc., depending on the value of x. So we're going to do a test that says, is our number divisible by, well, this k, by this incrementing number? And we have to repeat this test. Let's say in the kind of brute force approach we took initially, we're going to have to repeat it 6 times, 11 times, 10 times, in general, x times, to make sure that we've tested every integer from 1 to the number that we were given. Now this is where, again, we have different ways we can do this. This is the most brute force approach to do it. It's definitely not the most elegant. But what we can do is we're going to repeat this process over and over and over again. So this is where a loop is going to happen. So is k less than or equal to x? Now, when this is true, we want to then test, is x divisible by k? Again, k is going to be changing as we go. And if it's false, we're going to do something else. So k starts as 1, k is 1, it's less than x. Let's go by 6 just to kind of think this through. So let's say x is 6 as we're going through this. So 1 is less than 6. So what we want to do is, well, is our given number divisible by k right now, which is 1. If it is, we're going to do something. If it's not, we're going to do something else. So x divise by k. Right, so again, this is just a statement here. Is x divisible by k? It's a little bit sloppy here, but that's what that means. And again, this is going to go true or false. All right, so is x divisible by k? Well, what did we do when we were doing this by hand and asking this question? So like when k was 1, was 6 divisible by 1, evenly divisible by 1? Yes. So what did we do? We add k to our list, which is called LIS. And if it's not, well, we didn't really do anything. We just went on to the next statement there. So if it's false, there's really nothing to do. But there is another step. So we add k to the list when it's true. If it's false, well, we don't want to add k to the list. But either way, we're going to increment, and we want the next k. Because we want to try now, k is, let's say, 2, and then say, is our given number divisible by 2? If it is, add it to the list. If it's not, then we can move on. So next k. And really that's it for this step of establishing our list of factors. So when we do next k, this is going to loop us back to this question. Is k still less than our number? Because really there's no reason to test, like if our given number is 6, there's no reason to test 7 or 8 or 9 or 10 or whatever, because never are those going to be factors of 6 or x, whatever the given number is. So there's no reason to loop past, have a value of k more than our given value. So this way, or eventually we're going to terminate. Again, there's better ways to do this, certainly, but this will eventually terminate. It'll eventually come to the end. So this left grouping here is going to be our loop. So when it's true that k, this incrementer, is less than x, we're going to go through this loop and we're going to build this list, LIS. Now, eventually, we have to come out of this loop. What have we not addressed yet? We haven't addressed the other variable here, indicating the binary variable, is it prime or is it composite? So let's see here. We've established our list on this left side of the loop of this true statement. Now we're going to come out and we have to do steps here. At this point, our list is complete. So we are going to be able to return our list. So let's do our output. There's nothing else to do. So return LIS. We still don't know if it's prime or not. So how do we know if our number was prime? Well, when we did this by hand, we could see here when there were numbers besides the value x in general and 1, it was composite. And otherwise, if only 1 and the number itself were there, then it was prime. So here there were 4 numbers here there were 2, here there were 4. One way we could look at this is if any time there's only 2 numbers in the list, it looks like that means it's prime because the first number would be 1 and the second number would be the number itself. If there's more than 2, that means that we found at least one other factor. Let's do another quick test here, like 9. Is it divisible by 1? Yes. 2? No. 3? Yes. 4, 5, 6, 7, 8? No. 9? Yes. And again, looking at this list, there's 3 numbers here. Now, 9 was a perfect square, so there's 3, there's not 4, but there's more than 2. So it seems like if we have 2 numbers in our list, it must be a prime number. So we can look at a test here, and we can look at the value inside of lists. So we can say, does lists have 2 numbers? If that's true or false. So if it has 2 numbers, it appears as though it's prime. So we can now return another variable I'll call prim, again, not spelling prime, as 1. And if it does not have 2 numbers, then prim is 0. All right, so we return lists. We've returned prim with our flowchart here. But actually, let's take a look at kind of a unique case, see if our flowchart can manage it. And once we start coding, we can always come back to the flowchart, modify it if we need to see if it's working correctly. What if we give it the integer 1? Well, is 1 divisible by 1? Yes. And that's it. Is 1 prime, though? No, it's not. 1 is not a prime number. It's also really not a composite number. The problem statement, I guess, is not really thorough in that it's only giving us the options of prime or composite. So it's kind of poorly posed a little bit. So let's say not prime is going to be a 0. All right, so prime or not prime, most of the time not prime will mean composite, but I'm going to say 1 should return a 0, not prime. Okay, so let's just go through our flow chart here for 1. So x is 1, list is empty, k is equal to 1. Is k less than or equal to 1? Yes. Is 1 divisible by 1? Yes, add 1 to the list. And next k, we're kicked out of the loop because now k is 2 and x is only 1. All right, so list is done. It's just the number 1. Does list have 2 numbers exactly? No, it would only have 1, so prime is 0. So for the case of 1, actually our algorithm does work if we strictly require LIS list to have exactly 2 numbers. Then if it has 1, it's not prime. If it has more than 2, it's also not prime. Let's go through our example of 6 just to make sure in the flow chart it works. So if our input is 6, we'll establish an empty list here. Initialize k to 1. So is 1 less than 6? Yes. Is 6 divisible by 1? Yes. Put 1 on the list. Next k. 2. Is 2 less than 6? Yes. Is 6 divisible by 2? Yes. Add 2 to the list. 3. Yes, it's divisible. Add it to the list. 4. 4 is less than 6, but 6 is not divisible by 4. So we go down to false. Next, 5. Next, 6. 6 is divisible by 6. Add it to the list. Now k is 7. We exit the loop. All right, so we return our list. It's done. We have our complete list. Does it have exactly 2 numbers? No, not for 6. False. So we're going to return 0. It is not prime. So for a first version of our algorithm, this looks pretty good here. Again, not a unique way to do it. I'm going to make this empty list. We're going to see how we actually implement some of these things in code then. But it looks like we have at least a start for something that's going to work for us. So let's head into MATLAB and turn this flowchart into a program. But actually, before we get into that, let's think ahead a little bit. We have a loop in here. Let's see what's going to be put into this loop. This k is our indexing variable. We have a decision. We have an initialization. We have an increment. So those are kind of 3 ingredients that go into a loop structure. These 3 things here are going to lend itself well to a for loop. So I've marked them here. They'll all be incorporated into the structure of the for loop. We are not going to need individual lines that do each of these. The for loop will take care of initialization, incrementation, and testing. Now let's go into MATLAB and see how we turn this flowchart into code. Now we're ready to start coding this up. So we have our flowchart for reference, and we want this to be a function, so function, and we're asked to have 2 outputs. The list of our factors, LIS, I called in the flowchart, I'll match that here, and a binary is our input number prime or not prime. All right, so 2 outputs on the left-hand side, so we're going to have to give both of those out, and then the name of our function, so composite 200, L03, and I call this factors with a Z. Again, factors might be reserved, so this will make sure that it's not, even though I do have this composite 200 L03, I'll still call it factors with a Z. And we are going to give it 1 integer input here. And then the rest of the skeleton we'll have to finish with an end. Okay, so this is establishing our function. This will bring x into our function, so that first piece is done. Now I am going to establish list as empty. So I'm just going to put empty brackets here. I'm going to say that this is, as we go through, not the typical way if I'm making a list or a vector, which list is a vector here. typically I would not do it this way. I would pre-allocate it with zeros if I knew up front how many values it should take by the end of my loop. This is a little bit different a case. I don't know going in how many factors my number is going to have. So I can't really pre-allocate. I can, there's ways to do it. We can explore that. But right now I'm just going to keep adding to its value every time. So list is initially empty. Now I have this k is 1. As I said before, this is actually going to be inside or included in the loop itself. So my loop I'm going to keep testing is k less than x. So k is going to go from 1 by 1 to x. And it's going to loop that many times. Again, I'll put the skeleton together here. So that is our test condition. Is k the index variable less than x? Now we're inside our loop. So while this is true, we're on the left branch here. So now we have a decision. Is x divisible by k? This is a decision at this point, so it's an if statement. So is x divisible by k? Well, how do we test that? We've actually done this several times before. For divisibility, or we used it for even odd, the mod was a great choice for this. So if mod, so we're dividing x by k. So basically, if its remainder is 0, that means it is divisible by that number. So again, let's test it here. So is 6 divisible by 2? Well, we can look at its mod. It returns 0. Its remainder is 0. So that would be a true statement. So when it's true, we're on the left branch of this if statement. We want to add k to our list. So I can update. This is, again, a little bit different than how normally I would do this, because I would have list be indexed. I would have something like list of k equals something. This is a little bit different because it's not necessarily going to have a value for every value of k. K itself is going to be added to this list. And otherwise, else, that's if it's false, well, really nothing happens. So I can have this else here, or really I don't need it at all because there's nothing to do when this is false. We're just going to move on and we're going to have next k. So again, that's marked in green because that's part of this for loop. That next k is this middle thing here. It's going to increase the value of k by 1. So as far as the loop goes, this is actually really it. And actually, if you'll notice here, we have this red underline. It says list appears to change its size on every iteration of the loop. This is typically bad. It says this when you don't pre-allocate the size of a list and it keeps growing. Generally a bad thing to do. We'll see how we could address that as we go through. But for right now, I'm going to ignore that. I'm going to keep the warning there to remember to come back and fix it eventually. But right now, if it works, that's a great first step. Let's set it up before we go and fix it and optimize it. Okay, so the if statement is done. And actually, the whole left side, the true part of the loop is done. We are done with the loop at this point. So the for loop is done. Now we have to say, well, what happens when k is no longer less than x? So we're proceeding after the loop, which is really this, we can think of it as this false branch. Always, we're going to eventually go down this false branch. So that's, I'm going to add to 17. Once we're out of the loop, we're going to proceed with the rest of our code. So return lists, really there's nothing to do there. Automatically, that's going to be returned when we get to the end of the function. So nothing to code for return lis. Now we come across another decision point. Does list have exactly 2 elements in it? So this is an if statement. So does it have 2 elements? Well, how do we know how many elements are in something? We can use size, we can use length, we can use numL. I personally use length by default. That's not necessarily the best way to go, but is the length of lists exactly 2? If so, then it is a prime number. Prim is 1. And actually else, that's the false, prim is 0. So there's only 2 possibilities. the length of list is 2 or is not 2. So if it's 2, we're returning it's a prime number. Otherwise, we're returning that it is not prime. Probably composite, but not necessarily. And that's taking care of that if statement, and we're out of things to code. The flowchart is over. That end is going to return the values now of prim and of lists automatically at the end. So let's just make sure this is all nicely indented. This else we can have here, it doesn't do anything, so I'll just get rid of it. Because if the x was not divisible by k, well, there was nothing to do. So that else is unnecessary. Again, if we have it there with nothing after it, just to remember that we have, that the alternative is there's nothing to do, that's fine. It's not going to hurt the code, but it's unnecessary to have in the code. All right, so let's see if the function works the way that we think it's going to, and then we can go and we can clean it up a little bit. So let's take x is 6, so some of these test cases, and put it into our function. All right, so we run it. We have these two things to return, so let me actually run this whole thing. So for 6, we get the list 1, 2, 3, 6. That's what we got when we did it by hand, and prime was 0. It's not prime. Let's try 10, and let me run this so we can get our two outputs. 1, 2, 5, and 10, and not prime. 11. 1 and 11, and yes, it is prime. It returned 1, and that's good. And we tried 9. By hand, let's make sure we get the same result. 1, 3, and 9, not prime. All right, so it appears our function does what we want it to do. Again, not necessarily in an optimal way. We can clean that up in a second here as we look at this, but we at least have something that is working. So goal 1, complete working function. We've tested it with several different numbers. It appears to work. We could do a more thorough testing, but this does look like it's working. All right, so how can we optimize this further? So one thing is this list not being pre-allocated does slow it down a little bit. We should always pre-allocate if we're able to. This is a case where it's kind of hard to because we don't know how long lists is supposed to be. But we can get around that so that we can pre-allocate. So this is outside the flowchart, the algorithm at the time. So what I can do is think ahead to modify this. Well, the most numbers I could have in my list would be if every number were a factor. So like, I don't know, 2 would be a case where it's divisible by 1 and 2. So the list has 2 elements and our number was 2. But we can't have more elements in it than the number itself. So let me pre-allocate this with zeros. The length, x itself, by 1. All right, so let's play a little bit, just make sure this is working correctly. All right, so list is, I'm going to pre-allocate it to, in this case, 6, but in general, x values in it. So it is pre-allocated, but the way I'm using it down here, I have to change. Now, I'm not going to keep adding or popping on something at the end. It's initially zeros. What I can do is I could say this is more traditionally how I do use a list here is with this left-hand side using indexing. So list of k equals k. Let's just see what this does. It's not going to be right yet, but if I run this now, what do I get? All right, so it doesn't like that at the moment. Lists and let me just go in here. I'll just run this part for the moment, see what's happening. Okay, so for x is 6, just going in and running this section here, I get 1, 2, 3, I have zeros here, and I have 6. All right, so that's okay. But where's it giving me the problem? Let's go and check this branch here. That appears to be okay. So that's fine. Let's see. Let's see why it's not happy with it. All right, that time it is. Something might have just been kind of stuck here. So let's just see. All right, x is 6. Let's see what we're getting. And when we run our function, all right, it's giving us this list, which it has these zeros here, but that's okay. We can take care of that in a moment. And prime is 0. So it's still kind of working, and we've pre-allocated lists, so that's good. What if we try a number that is prime, so 11? Going through here, list is still broken a little bit, and it's thinking it's not prime because the list is 11 things long. It should only be 2 because these zeros are kind of bogus here just in the way that we coded it. But we can fix this. I can add something after the loop that's going to kind of correct these false zeros that were really just placeholders. What I can do is I can modify lists. I can say it is non-zeros of lists. Let's just look at non-zeros. There's other ways to do this more manually. Non-zeros is going to return the non-zero elements of a vector S. And that's exactly what we want to do here. And notice we can also use the find command to do this, but non-zeros is built in and it's going to be pretty useful. So let's just see what happens here. What does that look like? Oop, 1 and 11. Well, that's good. So this line 16 added is going to basically trim, well, it's not even a trim because it's from the middle, but remove the zeros from lists. And if we start putting in some comments here of what we're doing, and this is kind of matching, is x divisible by k? This is matching kind of the words that we had in the flowchart to see what we're doing at each of these different steps here. And going back. Okay, so now let's see what happens if we try x equals 11. Now that we put this pre-allocation in and this non-zeros, now we're getting it correct. Our list is 1 and 11, and it is indeed prime. Does it still work with 6? And does it give us the right list? 1, 2, 3, 6. It got rid of those zeros, and it's not prime. All right, so this has, in this modified version, we've pre-allocated, which is a good habit, especially when we have large numbers here. Because what if we made x equal to 658? Now it becomes more important that we pre-allocate because it's going to be running faster. Right, so now we have this longer list of things in here. Let me actually, it's going to be tough to see, but it will run marginally faster. This runs so fast, we're probably not going to notice a difference. But if I put in kind of a large number here for x, now it could start to slow down if we did not pre-allocate. And actually, we see it does actually mess up here. Apparently, zeros cannot be that large. I have too big of a number, so let me try a smaller number. I tried x was too big, and it didn't like that. All right, with a smaller number, okay. So you see here that this number has a lot of factors to it that I just randomly put in, and it is clearly not prime by all the factors that it has. And actually, we have one more optimization we can do here. If you notice, let's go back to a more sensible number like 24 that is divisible. If we look at the factors 1, 2, 3, 4, 5, 6, 8, or 1, 2, 3, 4, 6, 8, 12, then nothing from 12 to 24, and that's always the case. It will never be divisible by a number that is more than half of it. So another optimization we could do is we actually don't need to run this loop ever for numbers that are more than half of x. 24 cannot be divisible by 13, 14, 15, 16, 17, etc. So there's no reason to even test those numbers. So the end condition doesn't have to be the number itself. It's really half of the number is the last one we need to modify, or that we need to check. Now, this won't work as is. Let's debug this a little bit and see what's happening. So again, x is 24, and let's see what we get if we only check up to half of it. All right, so the problem is on list, we are not getting 24, which we know is going to be a factor of it. But that's okay. And it's not getting there because we're terminating this for loop early. But what we can do is we know that the last number of the list should be the number x itself. So that's what this line of code can do here. So put in the last element in list, that's what the end inside here means, the number x. Now let's try it. So we've fixed that small problem for, again, x is 24. This should do it. And it does. So let's just run this in pieces. Running just this branch, list at the moment has a 0 at 24, but we know that 24 and always the number itself is a factor. So running this line 16. Now if I look at lists, I've added 24. So now when I do a non-zeros, I am left with the proper factors. Right, so this is a little bit faster. I'm not wasting time checking a lot of numbers that I know are not factors of my number. So this is now at that optimization stage. And now, but let's check a number that like 15 and see what happens. All right, 1, 3, 5, 15, 0. So actually, it did work out in this case, but we can find an example where it doesn't. A problem we're going to have here is that this x divided by 2 is going to be 7.5, and that we would really not want to have a decimal value there. So it's actually only going to go up to 7. So actually this is probably not going to be an issue because we don't need to check anything that is larger than half of our number anyway. So like in this case, it's not going to check 8 for 15 as our input, and it shouldn't. So that's okay. What we could do here is I'm going to put in here a ceiling just to make sure that we're checking enough numbers here. So now that's going to, ceiling always rounds up, if I spell it correctly, or seal. Now it's correct. So ceiling will always round that decimal up. So ceiling of 7.5 goes to 8, just to make sure that we are checking everything appropriately. It was actually probably fine the way it was, but this will make sure we're not accidentally missing one of our values. And there's the last piece here. Now we were told we were given these integer values. We've only been using positive ones. Our code is not set up right now to work fully with any integer value. So if x is -8, let's see what happens here. If I try to put a negative number in, well, it doesn't work. Let's see where it fails. Oh, so list of end equals x. We could probably get this working. Let's just see, x is -8. So here's the problem is that I am having here zeros x. What I could do is actually modify this, and probably this can work with negative numbers. Let me put an absolute value in here. So that way, now we see that list is not empty. So that actually works okay. And now let's see here, we come down here. That's going to be -4. Let's also put an absolute here around the x, so that that's going to check this correctly. All right, so let's try again, -8. Let's see if the code works now. All right, so factors are 1, 2, 4, -8. So here we have, again, that same issue when we want to factor it. So let's put an absolute around that as well to add this in correctly and rerun our code. And we see here 1, 2, 4, 8. So it does work correctly with negative numbers as our input as well. But we hadn't even tested a negative number up to this point. But with a couple of modifications here, looking at where the errors were being thrown, we can modify our code away from that original flowchart, but modify the code to now work with negative numbers. And last, let's just check one more time for an input of 1 or -1. Are we getting the right values here? List is 1. It is not prime. And -1, one last test of our function. putting it in here. We get 1, and we get not prime for -1. So we manually went through this one time at the start to get an idea of what our flowchart should look like. We were able to create our flowchart based on at least the simple version of manually doing this. We used that flowchart to create a first version of our code, which did work. At least it worked for positive integer values, and we didn't go much further. Then we went through and started to optimize the code a little bit. We would really not see much of a difference in the timing for this one for at least small values of x, but we were able to reduce the number of iterations it has to run by noting that we never need to test a number bigger than half of it, but then we had to put in the number itself manually because otherwise it wasn't testing it. We were also able to put in a pre-allocation of our list where we can pre-allocate it as zeros, fill in only the values that were factors, and then use this non-zeros here to then get rid of those placeholders. And the pre-allocation is generally something we want to do. It's going to make our code run faster. So even though we kind of put in a bunch of these placeholders and then get rid of them later, it still technically will run faster than if we keep modifying the size of our list every time. And then we have our prime checker at the end. Is it prime or is it not prime? And everything appears to be working correctly. So we have our full function here. We have everything indented. We probably should have put in more comments as we went through, but we have something that's working and it's providing the service that we were asked for. 2 outputs, a list of the factors and an indication if the number that was the input number is prime or not prime.